A very good morning and welcome to this course on the foundations of continuum mechanics. Today we start with a new module on balance laws, and as a preliminary work we will be talking about material derivative of elements today to be able to write the equations in the subsequent lectures. So let us get started. So the topics for today's lectures are as follows. We will be talking about the derivatives of line elements, area elements, and volume elements. So in general, our approach will be first to write a relationship between the elements in the deformed and the undeformed configurations, and then develop a relationship between the material derivative of these elements with the elements in the deformed and the undeformed configuration. So let's get started. The discussion on the material derivative of line elements is mostly going to be a recap of what we have already done. So a line element dx can be written as f times d capital X, where d small x is the element in the deformed configuration and d capital X is the element in the undeformed configuration, and f is our deformation gradient tensor. So if I take the material derivative of d small x, which we write as a bar with a dot on top, this becomes f dot times dx. So in some cases I'll be writing a dot and sometimes I'll omit it, but both will mean the same thing. So the multiplication between tensors and vectors will mostly be an inner product in this discussion. And there's no term with a d capital X with a dot on top because d capital X does not depend on time. And we have shown previously that f dot is written as L times f. Then you have a dx. Again, I'm not writing a dot here. There's a dot here and here. And this f times dx is d small x. So this becomes d small x. So overall, we have the material derivative of the element d small x, that's a vector, is L times d small x. I'll call this an A, and this is something we already have seen in the past because d small x dot is nothing but dv vector, and this is equal to the velocity gradient tensor times d small x. In the initial notation, we can write this as dvi is vi comma j dxj. We have also showed that if we have the dot product of dx with the dx, that's basically the squared of dx, and we take a material derivative of that, this becomes twice dx vector dotted with the material derivative of dx, which can be written as twice dx, and we just showed the material derivative to be L times dx. So this can be written as d small x dotted with a 2L dotted with the d small x. And this we have shown earlier that this can be written as d instead of an L because the spin tensor W is skew symmetric, so that does not contribute to this inner product. In fact, we had shown a more general relationship earlier where we showed that the dot product between two vectors in the deformed configuration, the material derivative of that is d small x1 vector dotted with 2d dotted with d small x2 vector. So what we have shown, and we'll call this B, is a special case of that. So this was just to recall the relations for completeness. So now we move on to the material derivative of area elements, and this is something new. So let us say we have vectors d capital X1 and d capital X2, and they form a parallelogram in the undeformed configuration, and the area of this parallelogram in the undeformed configuration will be given as a d gamma with a knot on top to denote it is undeformed configuration. And when the deformation happens, these elements d capital X1 and d capital X2, they deform to d small x1 vectors and d small x2 vectors, which results in this parallelogram, and the area of this will be denoted by d gamma. Now we represent area as a vector. It is actually a pseudo vector, that is, under proper orthogonal transformations, it behaves mathematically like a vector. So d gamma naught is basically the cross product of dx1 vector and dx2 vector. And similarly, d gamma is a cross product of d small x1 and d small x2. So I can write these in initial notation as this, and in the deformed configuration, I can write the initial notation as like this. So I'll take this and proceed from here. So first we'll substitute these and these in terms of d capital X's using the deformation gradient tensor like this. And then we'll multiply both sides by FIA, and soon we'll see why we are doing all this. So this becomes FIA times d gamma I, and this is epsilon ijk. I'll club all the f's together, so FIA, FJB, and FKC, and then we have a dx 1b d capital X 2c. Let's look at this part, and in fact I will recall that the determinant of a matrix, let us say F in this case, was given as epsilon ijk, fi1, fj2, and fk3. So this is something we had discussed in the first module on background mathematics. Now here you can see that if I do arbitrary row exchanges in the matrix F, then more generally I can write this as epsilon abc times determinant of F, and that is epsilon ijk, fia, fjb, and fkc. So you put a equals 1, b equals 2, and c equals 3, you get the expression on the top. But if you do any row exchanges, that are taken care of by the ordering of the indices a, b, and c. So using this, we can write like this, and this determinant of F is nothing but the Jacobian determinant for our transformation. And also, if I go back and look at the expression for the area of the element in the undeformed configuration, this is what I have in my current expression as well. Epsilon abc dxb dx to c. So I can simplify the expression now. So j times d gamma naught. I'll write the definition of F. I'll write this as x I comma a d gamma I is j d gamma naught. Now further, I'll multiply both sides by capital X a comma q, that is the F inverse matrix. So on the left hand side, I have xi comma a times capital X a comma q times d gamma I, and the right hand side is j d gamma naught. Well, there's an index a that I missed. Remember, area is a vector, times capital X a comma q. Now this quantity is delta iq. You can see that if small x is written as a function of capital X's, this is nothing but the chain rule. So the left hand side simplifies to d gamma q, and that is equal to j times d gamma naught a times capital X a comma q. This will be boxed, and we'll call this C. Now I tell you what we have been doing. Basically, we're trying to express the area in the deformed configuration in terms of the area in the undeformed configuration. So all this was done for this expression. And symbolically, we can write this as the vector d gamma is the scalar Jacobian determinant times the vector d gamma naught dotted with the F inverse matrix. So we'll call this C1. And if I take an inner product of both sides by F, we get d gamma dot F, that's equal to J times d gamma naught. And we'll call this version C2, as we'll be working with these versions in this lecture. And now that we have an expression for d gamma in terms of d gamma naught, we will apply a material derivative to it. So when we apply the material derivative to C2, this is what we get. So first we have a d gamma dotted with an F. Then we have a d gamma vector dotted with an F dot. And this is equal to the material derivative of J times d gamma naught. Again, whatever's in the undeformed configuration is not a function of time, so the material derivative of that is a 0. Now to proceed further from here, we need an expression for J dot. So what we'll do now is we will park this equation and we'll try to develop a relationship between J dot and J. So there's an identity for any second order tensor A, and the identity says that the material derivative of the determinant of A is the trace of the dot product between material derivative of A and A inverse multiplied by the determinant of A. This can be shown easily using indicial notation. So I'll give you as a homework to show this using indicial notation, and we will take it as a given. So if we apply this for A equals F, that is our deformation gradient tensor, this becomes, and remember determinant of F is the Jacobian, so this is a J dot equals trace. Now F dot was shown to be L times F, so this becomes L times F, and then we have an F inverse. And again, determinant of F is a Jacobian. So this becomes trace of L times J. I can also write this as J dot is J, and the trace of L is nothing but Vi comma I. And we can also write this Vi comma I is the divergence of the velocity field. So all this I'll call equation D. So we'll be using different forms of D at different times today. So now that we have a relationship between J dot and a J, we can go back to our work. So coming back to our equation here, we can replace, now using D, this becomes, so we get this form. And now I multiply both sides by F inverse. So this is what we get. And remember, what we're trying to do is we're trying to express the material derivative of the area element in the deformed configuration in terms of quantities in the deformed and the undeformed configurations. So this is the reason that we have isolated this term here. So I can write d gamma dot as the trace of L times J d gamma naught times F inverse minus d gamma dotted, and now we have an F dot F inverse. So F dot is L times F, and F times F inverse is an identity, so this becomes L. Now look at this expression, and let's go back to our equation C. So if I look at C1 here, I can see that J times d gamma naught dotted with an F inverse is d gamma. So I can substitute this in my current expression. So this whole quantity here becomes a d gamma vector. So this is the simplified expression which we will call our equation E. I'll also box this because that is the relation that we wanted to get. Let's write this in the initial notation as well. So this becomes d gamma I, the material derivative of that. The trace of L is Vk comma k times d gamma I minus the dot product is d gamma j vj comma I. This we'll call E1. So as expected, we have expressed the material derivative of the area in the deformed configuration in terms of the area in the deformed configuration and the velocity gradient tensor for the deformation. So now we'll do the same thing for volume. So let us say we have three vectors in the undeformed configuration as this, and from these I can form a parallelepiped like this. And when the deformation happens, which is given by this function small x is a function of capital X, it results in three vectors in the deformed configuration as like this, and the parallelepiped that is formed is this. We can write the volume d omega naught in the undeformed configuration as, that is the box product or the scalar triple product of these three vectors, because the scalar triple product signifies the volume. And in the initial notation I can write this as epsilon abc d capital X A1, d capital X 2b, and d capital X 3c. And similarly, in the deformed configuration, the volume can be written as epsilon ijk d small x1I, d small x2j, and d small x3k. So like earlier, we'll start with this expression and we'll try to express d omega in terms of d omega naught first, and then we'll take the material derivative of that. So we write d omega as epsilon ijk, and now I express the d small x vectors in terms of d capital X vectors. So this becomes fia, fjb, and fkc, and then I write the d capital X 1a, d capital X 2b, and d capital X 3c. And again we can see that epsilon ijk times fia, fjb, and fkc is nothing but epsilon abc times the determinant of f, which is the Jacobian. And this part is nothing but d omega naught from here. So finally we can write d omega as j times d omega naught. This has to be boxed and we'll call it equation F. Or we can write the Jacobian being the ratio of the volume in the deformed configuration to the volume in the undeformed configuration. So this we'll call F1. So let us look at this expression for Jacobian that we have got. So from here, I can conclude that j has to be greater than 0, physically speaking, because if j is equal to or less than 0, that means my volume has either collapsed or become negative, which is physically not possible. And this is something we already have shown in a different way. Let's demonstrate that. So earlier we had shown during finite deformations that this ratio is the square root of the third invariant of the Green's deformation tensor C, which is nothing but the determinant of C square root. But C is defined as F transpose F, which implies the determinant of C is the determinant of F transpose F, which can be written as determinant of F transpose times determinant of F. And we know determinant of F transpose is the same as determinant of F. So this is determinant of F squared. So basically what we see is that determinant of C is determinant of F squared. So this becomes square root determinant of F whole squared. So this basically is determinant of F, which is the Jacobian. So we basically had shown this earlier, and now we are seeing this again. Now if my Jacobian determinant is equal to 1 for all x's, that is, the deformation is such that the volume does not change for any element in the body. So what I mean to say is that d omega is d omega naught for all volume elements in the body. Then we say that the motion is an isochoric motion. So isochoric means that the volume is constant. So now that we have established a relationship between d omega and d omega naught, we will now take the material derivative of d omega. So we get d omega with a dot on top, and that's equal to j dot times d omega naught. And j dot was shown as j times the trace of L from equation D, as we can see here. And then we have a d omega naught. So I can write the material derivative of my volume element in the deformed configuration as j times the divergence of velocity field times d omega naught. And this I'll call the equation G, because now I have a relationship between the material derivative of d omega and quantities in the deformed and the undeformed configuration. We'll also box this. Now, as a special case, if my motion is isochoric, then that basically means that the volume is not changing for any element. So if the volume is not changing, then my d omega dot, that's a time derivative of d omega, that has to be 0. And from equation G above, if the right hand side is 0, I can write that as j times divergence of V times d omega naught is a 0. But j cannot be a 0. We just showed that. And d omega naught also cannot be a 0. It's a volume. So this quantity has to be a 0 for my motion to be isochoric. So in terms of the velocity field, I have got a relation now, that is a divergence of velocity is 0 for isochoric motion. So in terms of velocity, if the velocity is divergence free, then the motion is isochoric. Or in terms of Jacobian, if the Jacobian determinant is 1, then the motion is isochoric. So with this, we conclude today's lecture, where we were able to find the relationship between elements, that is line, area and volume elements, in the deformed configuration and the undeformed configuration first. And if you noticed that the relationship was in terms of the deformation gradient tensor F, and the quantity L relates the rate of change of these above elements. So before closing this lecture, let us solve a quick problem. So the problem gives us a deformation, that is a chi function, with alpha and beta being positive constants, and we have to determine the relationship between these constants for the motion to be isochoric. For the motion to be isochoric, we saw that the Jacobian has to be 1, because d omega by d omega naught was the same as the Jacobian. So for this transformation, I can find the F matrix first as this, and the Jacobian is given as the determinant of this matrix, which has to be a 1. So we basically have to expand this determinant, which when we do, we get this equation. Now 1 gets cancelled on both sides, and I can take a beta common. So I get this equation. But alpha and beta are given to be positive constants. So beta cannot be 0. So this equation has to be true, which will give us the relationship between alpha and beta. So I can separate the beta terms on the left. So I get a beta times alpha minus 1 plus alpha squared is equal to alpha squared plus alpha. That gives me beta as alpha into 1 plus alpha upon alpha squared plus alpha minus 1. So this is the solution to this problem. So in the next lecture, we will talk about the transport theorem, which will form the foundations for writing the balance laws. So thank you very much, and I will see you in the next lecture.